Thank you, everybody, and thanks for the opportunity to talk. Thank you to all the previous speakers. I'm privileged to be part of the panel, and I'm going to take us in a little bit of different direction, but definitely have issues related to tolerance and basically accommodation for movement and creep and whatnot. So anyways, want to kind of just talk about some just general, overview, but then specifically talking about a case study, which was a job that we did a couple of years ago. This is the NEMA high rise here in Chicago. It's 74 stories and just about 900 foot tall. So some issues. And before I get into it, I just want to just point out a couple of things. It's a pretty neat structure. It's all exposed concrete. And one of the things that was a challenge was basically the tiered architecture. So you've got columns down here that are like only say 40 stories or even lower, 20 stories. And then immediately adjacent to it, there's a bay, there's a column that goes up all the way to the top, like 900 foot. So you've got like these, like at the lower part of the structure, you've got like a bay with one side, 20-story column immediately adjacent to a 74-story column that's 900 foot tall, and some of the challenges that went with that. So basically, just this is a McHugh experience. Our experience is that shorter concrete buildings, less than 40 stories, the process of constructing the building to theoretical elevation for each successive floor corrects much of the shortening column effects. So basically, we're not using a standard length rod and just building to that standard length every time. We're basically shooting into elevation. And that process of constructing, setting our forms to theoretical elevation is correcting some of these creep and shortening effects. And so therefore, they're not explicitly handled. Taller buildings are a different animal. And again, general experience, taller buildings are greater than 40 stories. Creep and shrinkage effects are real and are problematic and need to be explicitly considered and addressed by the engineer record and the contractor. And we'll talk about that. So just some really quick definitions, like what's creep? Creep is a time-dependent deformation of concrete under permanent loads, so dead load or PT effects. What's shrinkage? It's also a time-dependent, but it's a volumetric change that the concrete undergoes as it hydrates and free water evaporates. It's not load-dependent. Creep and shrinkage deformations are substantial. They can be up to 2 times the instantaneous deformation, and they really should not be ignored. So there's good references out there. ACI Committee 209, they published a document, and there's, obviously they expand on this, and there's other published literature out there. And I'm just going to quickly cover a bit of that. Some of the facts that, basically impact creep: concrete mixed proportion, high water cement ratio, more creep. Aggregate properties, they restrain the creep. So higher modulus of that aggregate reduces the creep. Age of the loading, early age loading increases creep. Curing conditions, better cure conditions reduce creep. Cement properties, higher F prime C, again, reduced. Temperature, higher average temperature, more creep. But the big one is stress level, most important factor. Higher stress, more creep. Factors affecting shrinkage, drying conditions, atmospheric conditions, i.e. humidity, lower humidity, increased shrinkage. So that basically to that point, based on the literature out there, if you had 100% humidity, you would not have drying shrinkage. Obviously, we don't, live in 100% humidity environments. Even in Chicago, which is relatively humid, we do definitely experience drying shrinkage. Shrinkage rate decreases rapidly with time. A third of it occurs in the first 28 days, 3/4 of it in a year. Water cement ratio, higher water cement ratio, more shrinkage. Again, this is just some basic information. Some diagrams that show this. So this is a nice diagram here that time on the x-axis, strain on the y-axis. Item number 5, the initial elastic shortening, so elastic movement. So basically, you get that movement when the load's applied. And then you have item number 4, which is that drying shrinkage. Again, it's a time-dependent thing. And then you have item number 3, which is basically a creep amount. And so you can see that the creep and the shrinkage are greater than the initial elastic shortening. Here's another diagram that kind of shows this. So for instance, you have a concrete element, you apply a load, you got elastic shortening, that's that delta 1. And then with time, you apply, maintain that load, you then have like these plastic non-recoverable shortening, which is due to the drying, shrinkage, and creep. Basically, by this mechanism, you can get the mechanisms for differential shortening for columns. So for like a heavily loaded column with a small cross-sectional area compared to a core wall with a large cross-sectional area with a reduced stress state, you can get differential shortening, or two adjacent columns like I was hinting at earlier, where you might have like a 900-foot tall tower or column adjacent to like a 20 or 30-story column. They might have, for that particular job, they had the same cross-sectional area, so you're getting different stress state and consequently different amount of movement. And again, some more diagrams that show this this concept of elastic strain, which is the top, creep strain, the second one, drying shrinkage, and then another third one at the bottom there is this guy right here, which we'll talk about a little bit, is thermal strain. That is a movement that we find is actually a noticeable and important term for exposed concrete towers, where you might have the swing in temperature between winter and summer, and the building's got to be able to basically ride through that. And more importantly, the cladding systems that are in that building got to ride through that. And then causes differential shortening, same idea. Like basically you've got an exterior column versus an interior column, similar areas, but you got different loads, and you're going to get different levels of shortening. So contractors, what do we want to do? We want to build fast, safe, and efficiently with the least amount of remedial work as possible. There's a disconnect between Division 3 and Divisions 8 and 9. 8 and 9 are like, cladding and floor finishes. Engineers designing buildings that are generally, they're taller, more efficient, slender, thinner, lightly reinforced, and more highly stressed, are more susceptible to deflection and creep than arguably buildings that were designed and built decades ago. And more importantly, we got a higher expectation of the design team and the owner for dimensional tolerance and structural movement that's kind of implicit in here. So pre-construction wise, like what do we do to try to handle all that or manage it? We obviously are making sure that everyone's understanding the project tolerances, and we're using ACI 117 documents. And then we're asking for and requesting from the design team, some input like on anticipated slab deflection, slab shortening, like slab edge shortening, column shortening, and column thermal movement. So we're asking the EOR for this information. And then basically looking for potential conflicts between the structure and the cladding systems and floor finishes. In particular, the window wall systems need to accommodate both the construction tolerances at short-term and long-term deflections and movement, and review the specifications. We're looking to make sure that the tolerances and anticipated movements are bought out in those other systems. So we want to build fast. We want to plan the work to proceed efficiently, and we want to deliver the structure that meets all the project specification requirements, and of course get paid, and try to avoid costly remedial works. In the state of Illinois, the statute of repose is 10 years. So we're out there for a long time exposed. And so obviously, if there's an issue that may crop up years after we've left the job site, it's a problem. So we're trying to, again, anticipate and plan and avoid. So we got the patented McHugh RFI launcher. And we ask questions. So this is a particular project, NEMA, we were working with our EOR, and they gave us this cool ETABS analysis results of their stage structural analysis, and they gave us some really cool information. Like for instance, the mass of the structure was such that it basically produced a lean southeast due to the unbalanced mass on one side. It was about 2.5 inches, or like H over 3,500, which is quite small. But again, we got this information. We made sure that our elevator contractor was aware of this. And again, this is not something we tried to correct as we constructed, but we were told ahead of time, hey, look out for this. And we made sure we bought that out. Here's another bit of information we got from the EOR, which was really helpful. Basically saying hey guys, you got these columns, architecturally, the columns all have the same cross-sectional area, and you've got certain columns that are going up, basically 900 feet. And then you have an adjacent one that's only going up 42 stories. So you've got this basically different stress state, and you're going to end up with significant differential column shortening. in this one bay. So this one bay is going to see like, 1.5 inch in column shortening in just that like 34-foot dimension. So it's quite, sorry, 37-foot dimension. So it's quite significant. So how do we mitigate that, or how to manage that? So asking the window system to basically ride through 1.5 inches was not really going to be a good solution. And also like that amount of being 1.5 inches out of level was going to be problematic. So the engineer came up with a program of basically introducing column cambering. So we constructed the columns and built them at a 3/4 inch above theoretical elevation, up to 3/4 of an inch. It varied as we went up the building. And again, we came up with we're prescribed a table by the engineer, and we're told to build it. But by using this column cambering mechanism, instead of having 1.5 inch differential in that one bay, we're able to reduce it down to 3/4 of an inch. And therefore, that would be within the limits of what the cladding system could ride through. And so again, this took a lot of effort, analysis, and collaboration with the engineer, and then sharing that with the window contractor. So this is what this basically proposed column cambering data that we're given to by the EOR. So he gave us this nice little key plan up here, and he's got like these identified columns. And then for these different columns here, he was basically prescribing that they were being built ranging from 1/4 inch above theoretical elevation to upwards of like 3/4 of an inch, and then tapering down. So again, this was based on the engineer's basically staged construction analysis and trying to balance balance out the anticipated movements to within a range the window system could tolerate. And so therefore, like this diagram here is basically showing the long-term deformation of the of the columns subsequent to casting at level 35. And basically it's saying like this guy here is there we go. Is anticipated to move like 1.95 inches. This guy is anticipated to move 0.56 inches. With the cambering, we were basically building this guy up 3/4, and we're able to get this difference down here to like 3/4 of an inch, which is quite good. Again, another way to kind of help visualize this column differential shortening, we're looking at the elevations, and these colors are basically kind of illustrating like, the zones of like, how much racking is going on, if you imagine. And so this guy right here was the most severe. So these columns here, the tall column had the greatest cambering to get that building movement into a range that the cladding system could basically operate within. So again, long-term movement. So we're basically talking about like 1.5 inches of movement over 37.5-foot span. So what was helpful here with this large bay was that we were able to basically break up the movement into individual panels of the windows, which I'll show coming up. So again, predicted thermal movement. This is another topic that we had to deal with. Basically, the building, as I said before, is exposed concrete. It goes through the extremes of Chicago winter through summer, and these columns are long. So you imagine a long concrete pavement that's 900 foot long. You're going to expect to see some movement. So consequently, have a 900 foot long column, you're going to definitely see also movement. So you're talking about columns that are going to basically have a change in basically almost 2 inches in length from extreme warm to extreme cold. So the delta temperature we were considering here in this analysis was about 62.5 degrees. Also, what was interesting here was the difference between a corner column and interior column. So you get this corner column here and this interior, basically this column here. It's this column here is cold or warm on 2 sides, while this guy is only cold or warm on 1 side, and that had an impact on the thermal movement. Again, it was pretty interesting analysis, and again, this is information provided by the EOR that we were able to then share with our window contractor. So basically, we had to make provisions for 1.25 inch thermal movement in our window system. And then, of course, we can't forget about slab deflections as well. And those are also impacted by creep and shrinkage. So again, the deflections for these big bays was actually quite modest, only about 1 inch, which is very, very good. But for the cladding system, we're looking at along the edges, looking for deflections there. So we're seeing about upwards of a 1/2 inch deflections of worst case. So what does this all mean for the cladding system? So we got basically a cladding system that's broken up into a series of panels, and it's got to ride through a bunch of movements. So you've got live load deflection type 1. So again, you've got basically full live load on the slab above, deflecting down 1/2 inch. And then so the window system is going to, the head has got to be able to accommodate that. Deflection type number 2. So we've got live load on the bottom slab here. And so these panels are moving down. So it's got to basically be able to accommodate this 1/2 inch movement. You've got column shortening that could be due to the creep and shrinkage as well as a thermal movement. We're talking about basically 1.5 inches here. And then you've got interstory drift, so the whole racking of the building. And so basically H over 500 or 1/2 inch maximum. So these are all the kind of movements the window system's got to do, and was able to be accommodated by the panelization of the windows. So here's another look at the building cladding system for a typical bay, 37.5 feet. Basically, how much movement we're thinking about we're going to get, and I've got a nice diagram over here of the mock-up that we used. So they built a full-scale mock-up of a bay, and they were looking at basically how this bay made up of these panelized windows would ride through the building movement. So construction tolerance, again, that's completely separate from the building movement. So obviously we fought and made sure that everyone was aware that the owner was getting ACI 117. So of course the slab could be up or down. So got this hard connection. Yeah, right over here. And then basically it can vary. And then this is this threaded bolt right here is making that hard connection to the embed. And then this is basically shimmed and caulked at the top side. Again, we have an embed right here with this threaded connection. And then we're basically shimming and caulking to accommodate that construction tolerance. But then we of course got to deal with vertical load deflection. So that's this basically the movement of the slab up or down. So we got like a 3/4 inch deflection, 0 deflection, and 3/4. So again, it's accommodated by this what they call the chicken head here of this window system. And basically this is a fully open condition. This is the gasket here that's got to remain weather tight or watertight. This is 0 deflection, and then this is it closed up. So again, the window system can accommodate both tolerance and building movement. And then here's a mock-up. We had it 2 stories. We had a bunch of actuators in there, and we basically went through a whole series of loading where we were applying different types of loads that mimicked the predicted building movement. And then this is a whole sequence of type loading. So we had position 1, we're just moving straight down, racking, and then we had basically pushing up and variations of other movements. But again, this was quite exhaustively developed and debated and worked on by the design team and the construction team to try to come up with the appropriate testing regime. And then here's some basically some pictures of some pretty massively awesome caulk that basically allowed the system to accommodate the building tolerances, and then obviously all the building movements is within the window sill piece and a head piece. And then slab edge shortening, that is also a thing that needs to be considered and has basically the result of creep and shortening. So, and this affects cladding, window wall, and brick, and can have impacts on the aesthetic of the exposed concrete at walls, columns, or where plumb windows meeting leaning columns can be an issue. Window frames highlight the slab shortening issues. So give you an idea, what you have to consider. This was some information from the EOR for a project saying hey, at the slab edge, immediately after casting within a week, expect after the PT forces the slab edge to have moved in 3/8 of an inch. And then at 28 days, it's just over a half. A year, it's 7/8, and in 5 years, 1.1 inches. So you can basically, and of course, then we have tolerance on that. So you can easily imagine a scenario where you can have problems with your cladding system. And so again, getting this information from the engineer record, and then making sure that the design team or the architect, as well as the window contractor and ownership, are all aware of this, and we plan to deal with it. So here's a concept, or basically just a diagram showing the concept of how we can end up with a displaced or leaning column, even though we're building everything to tolerance. So for instance, you have like step one right here where you've already constructed a floor or column right here. And this dash line is like a reference line. You constructed this PT slab. It's cast, it's unstressed. You've already, like on the next day, day one after casting, you're forming and pouring this column or putting it up there. And then step two, this slab gets stressed and moves to the left. And now all of a sudden the column that was placed here now just moves in. And then step three, you're now like putting the next level up here and you're putting the slab edge back at the reference line. And then now you're stressing it. And so now you got a leaning column. So again, this is sort of all exaggerated, but this is a real effect. And, you know, again, like basically talking about this concept and sharing it with the cladding subcontractor and the architect is important. And then here's some pictures illustrating some issues where this appears. So you got the slab edge right here, and it's shortened, and you can see that this slotted connection right here is fully maxed out. So it worked, but just. So again, here, this is another example. This is a slab. It was PT'd, and so this whole thing moved to the right, and this system right here, the window wall right here, basically this concrete had to be like notched to get that to work. And then here's another example of this slab edge here. It shortened and moved to the right. And now we're left with this ragged edge that we had to basically add it, like, you know, this cover had to be modified to cover that. But again, that's an issue of slab edge shortening. And then of course we got our guides and checklists, which are great resources. And we always like are, you know, encouraging our design colleagues and window contractors to be aware that, hey, you know, we're building to tolerance, but, you know, we owe tolerance. Which does not include building movement. So in conclusion, like, you know, RFI the EOR for anticipated deformations, better planning for deflections, column shortening, and tolerances equal less remedial work, cost savings, and happy repeat clients. And buy the same tolerances from all the trades. And as with everything, communication is the key to success. And with that, thank you.